All right, I'm McKinley,
I'm Rose. I'm Sydney.
and we're doing calculus of nature. We decided to choose this topic because we're interested in it, and there's a lot of different applications in nature, and I can argue, and I have argued, that everything in math comes from nature, but we can have that argument another day. But also, like this time, we wanted to look at a few things in nature that are just there, like Rose is going to talk about the Fibonacci sequence, and then also, a lot of times humans, we make models to better understand what's happening in nature, so we're going to talk about that as well.
So the first thing I looked into was the logistic growth model, which of course we already learned about. So the only information I could find that would be easy to apply to this was white-tailed deer in Kentucky. But so this is the equation they use, which is pretty much the same as we have. So the population was 900,000 in 2004, and it should double every 3 years, so the rate of increase should be 0.2311. And the average density is 27 deer per square mile, so I just multiply that by the square miles. And then I put it in the so then you just move the differential equation around and integrate, and so I graphed the population. You can see where the carrying capacity is up there. You really can't see the numbers, okay. So then I just integrated that equation and divided by 40, which was how many years, and I got the 1,052,578 average population growth per year. Next I did island biogeography, and in 1967, Robert MacArthur and E.O. Wilson proposed that the number of species on an island shows the rate at which species colonize it and the rate at which they go extinct. So the rate at which species become extinct on the island are related to the number that become residents. So after equilibrium is reached, the population stays generally around there, which makes sense. So like it just fluctuates around there, and it depends on the area of the island and the resources there. So this was the immigration rate, and they had this equation, and then for the extinction rate they gave that one. So you just make it equal to each other and solve for the S, which is the equilibrium. So that's the equation where I is the max immigration rate of the new species, P is the max number of species that can immigrate to the new island, E is the max rate of extinction, and this S is the equilibrium. The history of the metapopulation theory is the term metapopulation was coined by Richard Levins in 1969, and it was first applied to marine life. So an important contributor was Finnish biologist Ika Hansky. So the term metapopulation, it just means like a population of populations, so it's like a group of groups, I don't know. So it's made up of the same species, and it states that several distinct patches are stabilized by their proximity to other patches, and patches are just like the sections of the population. The change in the patches' inhabitants are given by this differential equation where P is the fraction of colonized patches, M is the average colonization rate, U is the extinction rate, and 1 minus P is uncolonized patches. So the metapopulation is stable when the rate at which recolonization is equal to the rate of extinction, which is kind of a little like the last one. But the rate at which recolonization occurs is proportional to the distance between the patches.
All right, so there's a ratio that occurs a lot in nature and in architecture. It's called phi, or other like historians and mathematicians have referred to it as the golden ratio. So Pythagoras originally kind of discovered ratios when he was listening to how blacksmiths hit their anvils on the metal, and he noticed that different sizes made different sounds. And so from that, he kind of figured out ratios, and he wanted to keep it a secret. So he only told like his brotherhood, and ironically, a pentagram was the sign of his brotherhood, which is also another place where phi is a huge important ratio. A pentagram, in case you don't know, it's a perfect pentagon with each point connected, so it forms a star inside. So like the long side of a star compared to like the 2 segments is the same ratio as the 2 segments compared to the short segment. And like everything in there has the exact same ratio. And then it's also used to construct a lot of Greek architecture, and ancient Egyptians actually used the ratio in constructing the pyramids of Giza. So here, if the diagonal was phi length, for example, and the side was 1, and the height was the square root of phi, you end up getting phi by the Pythagorean theorem. So yeah, it's known as the golden ratio. Another way that mathematicians have found phi is they would draw a rectangle and label the long side phi and the short side as 1. Then they partition that off to form a perfect square and another rectangle below it. So then you have two congruent rectangles, and I made them both the goldish yellow color so you can see which ones are congruent. So then the length of the short side is still 1, but now the long side is 1, and the shorter side is phi minus 1. So from that and all that congruent stuff we learned in 8th grade geometry, you can find that phi over 1 is equal to 1 over phi minus 1. So from there, I set it up to equal 0 and use the quadratic formula to find that phi is 1/2 of 1 plus or minus the square root of 5, but typically plus the square root of 5 is used, getting that phi is the ratio of 1.618. So from that second rectangle I made, you could keep partitioning off perfect squares and rectangles to form a spiral that is also known as a Fibonacci spiral. And then I just said how I think mathematicians would have estimated the square root of 5 is they might have used a Taylor series for the square root of x centered around x equals 4. Since when you plug in 5 minus 4, you'll have 1, and it's the easiest to work with the exponents. So another interesting thing about phi is that it's defined in terms of itself. So you can either have phi is 1 plus 1 over 5 if you do the math and you add 1 and then divide by phi, or you can have phi equals the square root of 1 plus phi. So that's if you take the square root instead of dividing. So that'll keep going on and on forever, making it super irrational. It's the furthest away from any simple fraction we've gotten so far. And I actually have a little sunflower activity to show that. Yeah. All right. Yeah. So here, you can plug in different fractions. In nature, like seeds and flowers, they have to rotate. These are different things by which they rotate by. If you plug in simple fractions or any rational number, they might spiral, but eventually they'll end up going out in a straight line since it's rational, or a simple fraction like that. But if you plug in phi, since it's not even close to rational, the seeds keep spiraling. 0.618. So for flowers in nature, like to keep their middles together, they would need to be round and solid, making phi the perfect rotation for those seeds. Alright, so then another thing that involves the ratio of phi is the Fibonacci sequence. It's found by, you start with 1, and then the next term is the sum of the two previous terms. So like I have the first two terms here. It goes 0, 1, 1, 2, 3, 5, 8, 13, and it keeps going forever. As you take the ratio between two numbers, so like, I mean, if you start with 2 over 1, that'll be 2, but then you get 3 halves, 5 thirds, 8 fifths, and eventually it converges to the golden ratio of 1.618. And then the pattern of this spiral is formed. So they have a square, say it has side length 1, then there's a square on top of it with side length 1, and next then they have side length 2, and like it's the side lengths that keep going with the ratio. And then what you do is you start in the corner of one circle, and it has one square, and it's a quarter of a circle in each square, and those quarter circles, since each side length gets bigger, they keep spiraling outwards for forever. So then a way Fibonacci explained his sequence was using rabbits. To do this, he had a few assumed conditions. One was that there were always 2 newborns and that it was 1 male and 1 female. Another was that rabbits are sexually mature after 1 month, and that every time a female rabbit gives birth, it gives birth to one male and female, and that rabbits never die. So after this, yeah, you see that they start not ready to reproduce, but then after 1 month, they're ready to have baby rabbits, but they haven't yet. So then by month 3, they're still there and they've given birth to another pair. Now while they're sexually mature, they keep reproducing every month, while that newborn pair right here, they have to wait a month until they can reproduce. And that pattern keeps continuing until after 1 year, you'll eventually have 233 rabbits, or pairs of rabbits. And here's just some examples of the Fibonacci spiral in nature. In the pattern of hurricanes, you can typically see it looking at them from above. And the same with like shells on animals. They're not always quite this perfect, but they do exist if you look hard enough for it. And then another thing, kind of like the sunflower, that plant, to let maximum sunlight in, leaves have to rotate. So what they rotate by is phi, so they let the maximum sunlight in. And then it's also seen with tree branches. So the Fibonacci sequence especially, as each one is there for longer, another branch breaks off. I like comparing it to the rabbits personally.
Alright, so now I'm doing the Latka Volterra model, and I'm actually going to grab that back up. Latka was Austrian, and they both discovered, just like Leibniz and Newton, they discovered it independently, but this time they discovered the model that presents two populations and puts them together in a single model. So they do a prey-predator population. And I'm actually going to stay back here because I'm going to show you guys a little thing that I was working on. So these are the two pictures that I'll end up showing you guys, but I'm going to show you how you find them. This one here is it's a vector field. So it's just like a slope field, but instead of it being using a function, instead of it being related to time, this is your predator and this is your prey. And I actually have my prey up here, my predator down here. But they're in relation to each other, no longer in relation to time. But then when you put them in relation to time, you get two graphs that look a little bit sinusoidal. So I'll show you guys here real quick what we got going. So keep in mind those two pictures because those are what this will bring up. So first I'm going to show you how to get that circle one. So what I have in here is just two equations. This equation right here is the predator population, and this is the prey population. The reason you know that it's the prey population, because the two prey is y2 right here, and predator is y1. And you can tell that anytime the predator and prey right here, they're meeting each other. So they're multiplying each other, they're meeting each other. And that's negative. You see it's negative right in front. That means that the predator is eating the prey at that moment. And obviously this one's positive because the rabbits, in this case, do nothing to the foxes when they meet each other. It's just only the foxes lead the rabbits. So the fox will continue to increase in population size. So what I got here is I'll just plot these two populations next to each other, and we get something like this. So this is a lot like that other graph we saw. It's a vector field. And what I did here is I had a starting population of 150 rabbits and 150 fox actually, and 100 rabbits. If I change this number here to 80, we'll get another part of that family here actually. I have to hold this graph so the graph stays on. And then I run it again and we get another piece of that family. So as you change your populations, you're going to get a different graph, but it's the same graph, it's just proportional, larger or smaller, depending on where your populations began. Now I'll show you what it looks like when you just let it so that it does itself off there. I'll show you what it looks like when you put it in relation to time. So I'm just going to take this out of a comment, and all I did here is I same two graphs, but instead I added this variable here, I added t. So I added time in here to allow itself to run itself on time. And this again, when you change your population here, say go back up to 150, it's going to be a family there, but it'll be a little bit different. So they're looking a lot the same, but they're a little bit different. And I'm going to explain it when there's only one graph here. Here we go. So right here, you can tell that the rabbits are the red graph, the fox are the blue graph. And so you can see that when the rabbits are at their max, the fox is just beginning to increase. So this is a change in population. So it's not population, it's change in population. So it's the derivative of the population itself. When the rabbits are at their max, they're at their max population because their derivative here is 0. The fox population is just beginning to increase. And this is because there's so many rabbits that fox can have a little fest on all the rabbits in there. But when the fox reach their max, now the rabbits are down in the bottom. So the rabbits are now, there's so many fox that they've eaten too many rabbits. And now this is what you call, this point right here in both of these populations is your carrying capacity. It's your carrying capacity when you no longer have enough, when your change in population goes from positive to negative. The only reason the logistics growth that Sydney showed, it kept going up, and then it kind of sat at that carrying capacity. The reason this is different and the reason why it's why it's so special is because it has the two populations, so it doesn't allow it to stay up there, because if it's to stay up there, you would need to have infinity amount of resources. But our populations don't have infinity amount of resources, and now they have predators as well. So that's why they start to come down. Now I'll show you something that happens when we begin to harvest or hunt. So if we're hunting animals, so we'll say we're hunting fox. What we're going to add here is we're just going to add -1. And this counts for 1 fox per unit of time. And what we're going to do is we're going to show you in the circle form. And what happens in that circle form is time is arbitrary. So time, which is weird to us. We always do go in time, but time really doesn't have a play. It has a play, but it's not shown in the graph itself because the only populations, or the only variables are the two populations. So what's going to happen here, if it'll come up, it didn't come up right. What'll happen here, what should happen here, is we'll make it so that, oh man, I tell you. Anyway, so what happens here is it'll do the same type of graph that we saw, the circle graph. And if I could show you, it'd be super cool. Because I almost cried last night when I figured it out. It makes this graph. But what happens is it starts here, and the graph is actually bigger. So what happens is it comes up and it spirals out. So it's going to spiral out like this. And when your population is the least secure, when it's the most fragile, is when it's the closest to these lines. Because this is when the rabbit population is super close, it's barely changing. So it's really close to falling extinct. This is where the fox population is barely changing, so it's close to falling out of existence. And so it keeps getting closer and keeps getting closer, and ultimately in those graphs, when there's hunting involved, they'll stop. So that's the idea behind needing to limit and control the different uses of hunting and things like that, and that's how wolves and deer and those kind of things, humans play a huge role in their populations, and these graphs are a good way to see that in a logical sense for humans to understand. This next quick one I'll show you here is the same idea. This one's in relation to time, but I added turkeys. So now these are 2 prey. This is another prey here. When I run this one, we're going to get, we'll get 3 graphs. And so what we're going to get here, fox are at their max when the 2 prey are, fox are at the max when the 2 prey are just getting to their minimum. But then without outside intervention kind of thing, like a hunting situation, slowly the populations begin to balance. So you can see it here again. The minimum of the fox is the maximum of the prey. but you see here that the fox the prey follow what the fox does. So the fox population dictates what the prey population is going to be. Here again, you see another max and a min of the max of predator, min of prey. And then coming over here, you have very little change. And the only reason this can happen, so right now what's happening, it looks like you have a constant population, but really what we have is a constant increase of population. But this constant increase of population controls this constant increase of population because your predators eat your prey. And so they keep each other in check, and that shows the strength and the flexibility of ecosystems given that there's limited outside interference into their life cycle and things like that. So those are just three pretty simple ways to look into how to look at populations in a given ecosystem. And I'm going to try this one more time because I want to show you guys that, but if it doesn't work, then that's that. What I'm going to try again is see if I can get the, no, it didn't work. I was going to see if I could get the line to come up. But that's what shows the different populations in the ecosystem. So those are our topics on calculus in nature. There's a few, these are just basic applications. Like we talked about, finding populations, predicting populations. That's a lot of the Latto-Volterra model. Designing buildings with phi, and then finding logistics growth and functions that are used in models. The key to models in nature is letting humans see what we can't see in an ecosystem. So that's calculus in nature. Any questions? Yeah.
So with the golden ratio, in terms of, you brought up like Greek architecture and such,
Yeah.
are there documents that say they use that, or is it just one of those things where they look at it and we're like, hey, look, it's a spiral?
It was a little bit of both. It wasn't like the spiral necessarily, it was the length was 1.618 times longer than the height in the Parthenon, I know was one. I just had trouble finding a good picture that showed it because they were all kind of hard to understand. And that was the biggest one that came up for sure. And I know it said the Egyptians used it on purpose, and there was one website that said it was a sacred ratio. And yeah.
I have a few questions.
Yep.
Wait, how many years?
Just, I wasn't here yesterday, I feel a little bad about that, but one thing that I like about these presentations is how much I learned, and it was really cool. The cool effect is really, really high. Can I go to, I think it's Sydney's, and you showed a graph, and I think it's the graph, that one right there. It looks to me a lot like an economic supply and demand graph.
That's what I did when I first saw it. Yeah, because then it goes to the.
So did you find any relationship between that and this, like any connection at all?
No, I didn't really look for that.
Okay.
But it does make sense though, because as you get more money in one place, you need to make more food or whatever. But as you get more species, you need to have more of the other resource. So it's the same idea.
Then can we go to the golden ratio? And I think it's where you do the calculations of the golden ratio.
Maybe that's the next one.
Yeah, right there. So, one of the things, that 1.618, that's the golden ratio,
Yeah.
correct?
Like,
You end up having two factors from that quadratic. Do you know what the second factor is?
it's like 0.382, and it is, I know 1.618 is the one that's used.
Yeah, because
more
one's
often.
gotta be negative.
Yeah.
One's positive, one's negative.
Well, it's still positive because the square root of 5 is bigger than 1. So you end up with 1 plus or minus the square root of 5.
Oh, yeah.
So-
Okay.
No,
So that's what,
yeah.
that's what you
It's
get,
negative.
you get, right, so you get, that's your negative factor, right,
Yeah.
when you're subtracting the square root of 5, okay. And do you know if that's used at all, that other factor?
Nothing that I've seen, because majorly it's been with like architecture, and you can't have negative materials.
When you said estimate the square root of 5 using a Taylor series, did you see that?
I didn't see it, that's what I would have done personally, because I don't know.
Did you
People didn't
attempt
have
doing it?
calculators. I did, and then like I messed something up, like I forgot to put it over the factorial, but
So
when
was your function the square root then? F of x equals the square root of x?
yeah, and then I put it around x equals 4, so
Yeah.
you would have had 5 minus 4, that way
Yeah.
1 to any power is still 1,
Okay.
and you didn't have to figure it out with like 0.001, because
Yeah.
then you would have been back at the same problem
Yeah.
without having a calculator.
And you messed up somewhere along the line?
I just forgot to put the factorial in there, but like even without that, it was still extremely close. I think I had 1.62 something.
That would have been really, really cool addition to that. That's where you're, that particular part. And then let's go to where you had Fibonacci sequence. I like that transition from the golden ratio, and then you showed Fibonacci sequence. If you create ratios out of them, like I wrote down 13 out of 8, 21 out of 13, 34 out of 21,
Yeah.
55 over 34.
The bigger the numbers get.
Yeah, and the closer and closer it gets. Did you say anything about a proof for that?
I
Or-
didn't see a proof, I just kind of,
Okay, so is there a general series notation for that, or?
there is, but you need the previous term to
Okay,
find
so-
the next one.
Okay, so I know there is an equation for the Fibonacci sequence. I think it took them like 125 years to figure it out. So I was wondering if you saw anything dealing with this particular sequence.
This is the one I saw the most, it was
It's a
like had the
recursive
n
one.
minus 1, and yeah.
The recursive's a lot easier, the other one is really horrid. Then, let's go to predator and prey, the diagram. Okay, those diagrams. So I'm trying to wrap my head around these diagrams. They're really, really cool. And why, who came up with the idea that to multiply predator and prey?
See, and that's why this is so interesting, is because Bata and Volterra both did it individually, but if those two things are meeting in real life,
Yeah?
they need to be dependent upon each other in the equation. So at that part of the equation, like I showed you in that, where you can see that it's negative because that's the prey population.
Mm-hmm.
Since whenever bunny and fox meet,
Mm-hmm.
then they lose bunny. So, and ultimately,
Yeah.
so the hard part about this is this is bunny population.
Yeah.
This is bunny population. This is bunny population.
So it's recursive.
Correct, and that's I think one of the keys to like fitting it all together is the easiest Fibonacci sequence is recursive. The things that come out of nature are all based upon what happened before them.
Yeah, and I think in this presentation, if, this is something I have to talk to the class later on, is I would emphasize the recursiveness of your talk here, the
Mhm.
presentation. And really that's the link
I just fixed
of all these together. Oh, you got it.
So this
All
is-
right, because that's my next
Yeah.
question.
This is the hunting. So if this circle kept going and closed, that'd be your typical predator-prey population. But what happens when we're hunting them is the changes happen more drastically. So you can see, so it's changing, and it would be changing normal, but instead it's going to change greater.